Good morning, physics guys. I just wanted to take a moment to talk to you about the answers, and it's real hard to read the text on waves and understand that is the be all and end all, and I know the answers right away. Um, I almost wish you could have just gone ahead and taken the answers from the solution manual and try and go backward and figure out if that's what you read. Um, so I'm going to do almost something like that. I'm going to read the question. I'm going to give you an answer, um, sort of give you an answer key to the questions you just answered, because I want you to be able to understand these waves. And waves are a little bit annoying because it's not an intuitive thing. We don't see waves on a regular basis. We see um, how gravity works, we see velocity, we see acceleration, we understand force, and we understand all those things that we've talked about before. We understand gravity because of the way things fall and the way the planets are moving in the sky. Not necessarily so much the planets, but we can see certain things. Now, waves we can see, but we see two different parts of a standing wave when we look at strings vibrating. And so I'm going to go through the questions, and then I'm going to go ahead and give you answers to those to the questions that are in the book. I have them on my other computer screen right here. I'm sure you see the reflection in the whiteboard. So the first question was, which characteristics uh, uh, remain unchanged when a wave passes through a boundary into a different medium. Um, and they sort of showed it to you when they were showing the picture of the two different springs. And I think I explained this in another video. The wave, stays up, and it goes through a thicker spring into a thinner spring, and you notice when it hits that boundary between the two springs, it still continues on. And so it continues on, but it doesn't have the same, all of the same properties. Now, the only thing that doesn't change when you're talking about a wave that crosses through a boundary is the frequency itself. Anything else can change. The amplitude, the wavelength, and the speed or the velocity can all change when a wave crosses through a boundary. And that's really the big idea of that one simple question. But is it necessarily laid out perfectly in the chapter? No, and yes. I mean, that's what it said, but it was really hard to find that right off the top. The second question was, it was all about refraction, and it says, can two-dimensional waves cross through a boundary between two media without changing direction? And this was a big one. This was, I don't even know if it was really explained heavily in this section, but I want you to think about light. Light can pass right through a window and not change, right? You see, when you look out a window, you see the reflection of light off of objects outside every day. If I look out this window right now, I see the tree in my backyard. And that's because light is reflecting off that tree, or that tree is absorbing certain parts of the light and showing up green in places and brown in places, and that's how light works. But when I see that light coming through the window, it does not change any direction. And that's really, we call that transmission, and there's reflection, and there are other parts and refraction. We like to talk about how waves change, and there is a possibility of passing through a medium and being transmitted straight through without changing. Now, the idea of not changing is the light being normal to the window surface, and normal being perpendicular. We talk about, the normal force is that perpendicular force. So when we talk about something that's normal, it's perpendicular, it's straight at it. Yes, you can see things at an angle out a window, but sometimes when you look through a window and you look up at an angle, it's just a little bit tilted. It's been refracted ever so much, depending on the thickness of the glass and the type of glass. So yes, it is possible. That's the answer to the second one. I think it was number 28. So it is possible to pass through without changing direction. Standing waves, and I'm going to do a little bit of demonstration on standing waves, and then I'm going to use what I've drawn to show you the answer to the last question. A standing wave is this, and I don't know if the explanation was as good as it could have been. I've since looked for other videos to drop on you, but you guys mostly don't watch the videos that I post anyway, and you're probably not watching this one. But I wanted to make this available so you could get the full understanding, because some of you really want to understand what we're talking about in this class. So a standing wave has to meet some requirements. A free wave is me talking and the sound going out, and that's it. But a standing wave is like a piano string or a guitar string, anything that's fixed at both ends. So it's not allowed to move on either end. So you talk about this, and I'm going to make it real short for now. So I have 2 points that I've fixed, and I have a string, any type of string, and I'm going to pluck the string. Well, if I pluck the string, then I create a wave. There are other terminologies that go with this, but I want to talk about the fixed ends. The fixed ends, these are called nodes. All right, and all the node means is that it's not moving. It's at its relaxed point, or its not moving point, and we've created this wave that goes from here to here. All right, and that's that primary wave right there. And once this wave gets over here, it's going to get reflected back. All right, and when it gets reflected back, it gets inverted. So as long as this point is fixed, this wave is going to be reflected back. And it's actually going to be the same. So I wish I could draw right, but it's going to be reflected back at the same, with the same amplitude. All right, and it's going to just keep bouncing up and down just like that. And so these points up here of amplitude, these are called antinodes. This is an antinode. Sorry about that A there. My horrible writing when I don't have anything, when I have 2 things in my hand, I guess I can't write. But so nodes and antinodes. And then I'm going to show you what happens when we have more going on. Let's say we have one entire wave throughout this string, right? And let's say the string is uh, 40 centimeters or 0.4 meters. So halfway through 0.2 meters, it comes to that rest point. And so now this is a node. And then it will be reflected back. Just like that. And we can add more waves to this and increase the frequency. But this is the picture that we want you to understand about a standing wave, is that it starts out, it gets reflected back, and here are your antinodes, an antinode and an antinode, and there are 3 nodes. And so that answer to number 29, it says, in a standing wave on a string fixed at both ends, how is the number of nodes related to the number of antinodes? And obviously we see it has 2 antinodes and 3 nodes here. So you're always going to have 1 extra node because it has to be fixed at the other end, right? You have it fixed here. It gets to that fixed point, another fixed point, and the 2 fixed points at the end. It gets to that medium point, and two antinodes, 3 nodes, 1 extra node per wave on a fixed string. So that's a standing wave. It looks like a standing wave. It's a standing wave because it's fixed at both ends, and it looks like it's sitting still when you're shaking it. And then I think that's what I mentioned in the other video. And last but certainly not least, I wanted to show you the examples that they were talking about in the last question. In the last question, they had a string with a wave running through it, and it was on its way here, right? And then they also had another wave coming the other direction. So the wave was going this way. And I think that I made a mistake. I think the first example was they were both above the line. So they were both the same type of wave. And then when they came together, they created a larger wave. Their amplitudes multiplied. And then you would see the same type of picture once they came together and left, right? So on the way in, they come together, they create a larger wave, they double their size when they come together, but then when they leave, they look exactly as they did previously. They're just going in different directions. And so this is the boundary where you're supposed to cover it up with a piece of paper. And I'm just going to take some random piece of paper that I have sitting here. You're supposed to cover up the sides. And you're going to see that the wave looked the same on both examples right there. And so when you have the one waves that are both sitting on top, it looks like it's just a wave that's running away and looks exactly the same. It passed through a boundary, it transmitted, it was the same type of wave. Whereas in the second example, you had waves, one on top, one on bottom, And when they came together, we had a flat line when they hit the boundary at the same time, when they hit each other, when they disrupted each other, and then this one continued on, the one underneath continued on, and this one continued on this way. And you were supposed to say that when you covered this side up, it was just a wave that hit a boundary and went back and was reflected back. And that was the big idea. We didn't talk too much about reflection. I didn't talk too much about reflection. I said reflection, it goes that way, it hits a boundary and it comes back at me. But I don't think I said when it hits the boundary and gets reflected back, it's going to be inverted. And so just like the standing wave gets inverted, if there's a fixed boundary that sound hits, it does get inverted and come back the other direction. So I think that's what will settle some of your questions. And if not, let me know and we can talk a little bit more about it. I'm not going to do a whole lot more on waves. I want to go back now and start our major review for the end of the year. I mean, it is getting close to the end of April, and the end of May is when we're finished. So I want to take a good 3 weeks and go over and do some exercises that will remind you of everything you're going to need to know on a final exam, because it's going to be pretty extensive. Extensive because you're going to be at home. I can't expect you not to use resources, so I'm going to make it a little bit more difficult, a little bit more challenging this year, and so not going to throw a whole lot more new information at you, but waves are very, very important. So thanks for your time, and we'll see you on the other side.